The night sky feels familiar. We grow up under it. We name the stars. We draw lines between them and call them constellations. We build myths, calendars, and nations beneath that same scattered light. And yet, despite thousands of years of watching the heavens, we are still standing at the edge of a question so large it almost breaks language itself. How big is the universe, really? Not how far we can see, not how far our telescopes reach, but how much universe actually exists. Because those are not the same thing, and for most of human history we quietly assumed they were. Then we built machines powerful enough to challenge that assumption. We learned that the universe has an edge we can see, but not an edge we can touch. We learned that space expands faster than light can travel. We learned that most of what exists may already be forever unreachable. And now, with the James Webb Space Telescope peering deeper into cosmic time than any instrument before it, something unsettling is becoming clear. The universe is not just larger than we imagined. It may be structured in a way that makes its true size fundamentally unknowable. What James Webb has revealed is not a number. It is a limit, a horizon, a reminder that the universe does not owe us completeness. And that realization changes how we understand everything from the birth of galaxies to the fate of reality itself. If you enjoy slow, thoughtful journeys into the deepest questions science can ask, take a moment to subscribe to The Boring Universe. Like the video if you want more long-form science documentaries. Leave a comment to support the channel and tell us which part of the country you are watching from. Before we can talk about what James Webb has revealed, we have to confront a problem that sounds simple but is anything but. When we ask how big the universe is, we are really asking several different questions at the same time. How far can we see? How far does matter extend? How much space exists? And whether the universe even has a size in the way we intuitively understand size. Human intuition evolved to throw rocks, build shelters, and navigate landscapes measured in miles, not in billions of light years. So when we project those instincts onto the cosmos, we end up with mental images that are comforting but wrong. For centuries, the universe was imagined as a kind of cosmic room, with stars fixed like lamps on a ceiling. Even after we learned that stars were suns and that galaxies existed beyond our own, the idea of a finite, knowable cosmos lingered. There must be an edge somewhere. There must be a wall, a boundary, or at least a last object beyond which there is nothing. Modern cosmology has dismantled that picture piece by piece. The first step in understanding the universe's size is recognizing that we do not observe the universe as it is now. We observe it as it was. Light takes time to travel. When you look at the sun, you see it as it was about 8 minutes ago. When you look at the nearest star beyond the sun, you see it as it was more than 4 years ago. When you look at distant galaxies, you are looking billions of years into the past. This is not a metaphor. It is a physical delay built into the structure of reality. The universe has a speed limit, and that speed limit is the speed of light. James Webb does not break that limit. Nothing can. Instead, it uses that limit as a tool. By capturing extremely faint infrared light that has traveled for more than 13 billion years, Webb allows us to see galaxies that formed when the universe was less than 1 billion years old. In doing so, it shows us not the edge of space, but the edge of time we can observe. This distinction matters because the observable universe is not the same thing as the entire universe. The observable universe is defined by a sphere centered on us, with a radius equal to the distance light has been able to travel since the Big Bang, accounting for the expansion of space. That radius is about 46 billion light-years in every direction, which means the observable universe is roughly 93 billion light-years across. That number alone is staggering, but it is also misleading because it tempts us to believe that beyond that sphere there is nothing. In reality, beyond the observable universe is simply more universe whose light has not had time to reach us and may never reach us at all. The universe is expanding, and that expansion is accelerating. There are regions of space receding from us so quickly that even light emitted today will never arrive. Those regions are not gone. They are just causally disconnected from us. This is where James Webb enters the story in a way that quietly rewrites our assumptions. When Webb began sending back images of the earliest galaxies, astronomers noticed something unexpected. The universe appeared to have formed large, structured galaxies much earlier than existing models predicted. These were not small, chaotic clumps of stars barely holding together. They were massive, surprisingly mature systems appearing only a few 100 million years after the Big Bang. This does not mean the Big Bang model is wrong, but it does mean that the early universe may have organized itself faster and more efficiently than we thought. And that has consequences for how we think about the scale of everything. If structure can emerge this quickly, it suggests that the processes shaping the universe operate on scales and timescales that challenge our simulations. Those simulations are not arbitrary. They are grounded in measurements of cosmic background radiation, the distribution of galaxies, and the behavior of dark matter and dark energy. But every model depends on assumptions. James Webb is now testing those assumptions in the most unforgiving way possible by showing us the universe as it actually was, not as our equations predicted it should be. And the deeper Webb looks, the more it suggests that what we see may be only a small, biased sample of a much larger reality. To understand why, we need to talk about cosmic inflation. Inflation is a theory that proposes that the universe underwent a brief but extreme period of expansion fractions of a second after the Big Bang. During this period, space itself expanded faster than the speed of light, stretching tiny quantum fluctuations into vast cosmic structures. Inflation explains why the universe appears so uniform on large scales and why regions that should never have been in contact look remarkably similar. But inflation also has a strange implication. If inflation occurred once, it may have occurred many times. Some versions of the theory suggest that inflation never completely stops, creating an eternally inflating multiverse where our observable universe is just one bubble among countless others. James Webb cannot see other universes, and it cannot directly test eternal inflation. What it can do is examine the fine details of early galaxies and the distribution of matter in the young universe. These details act like fossils, preserving information about the conditions under which the universe expanded. If those conditions point toward inflationary models that naturally produce vast, possibly infinite expanses of space, then the size of the universe becomes not just large, but conceptually unbounded. Not infinite in a careless, hand-waving sense, but infinite in the rigorous mathematical sense that no matter how far you go, there is always more. This is where the phrase, actual size of the universe, becomes both powerful and misleading. There may be no single size to reveal. There may be no final measurement to announce. Instead, what James Webb is revealing is the structure of our limits. It is showing us how much of the universe is accessible to observation, how quickly that accessible region is shrinking relative to the whole, and how much lies beyond any possible experiment. In other words, Webb is not drawing the boundary of the universe. It is drawing the boundary of knowledge. To appreciate how radical this is, consider how science has historically treated limits. Every major expansion of knowledge has been accompanied by the belief that the next horizon would be the last. Once we mapped the Earth, we thought we understood our world. Once we mapped the solar system, we thought we understood our place in space. Once we discovered galaxies, we thought we were approaching the ultimate scale. Each time the horizon moved, James Webb is continuing that pattern, but with a twist. The horizon is no longer just far away. It is fundamentally enforced by the laws of physics. There are parts of the universe that are not merely unknown, but unknowable, at least in principle. This does not make science weaker. It makes it more honest. The universe is not obligated to fit inside human curiosity, and yet within those limits, there is an extraordinary amount we can learn. Webb's observations of early galaxies are refining our estimates of how matter clumps, how stars ignite, and how black holes grow. They are helping us understand how quickly complexity arises in a universe governed by simple laws, and they are forcing cosmologists to reconsider how representative our observable patch really is. Imagine standing in a dense fog with a flashlight. The beam illuminates a sphere around you, and within that sphere, you can study every detail. You might map the ground, measure distances, and infer patterns, but beyond the reach of the light, the fog continues. The landscape does not end. Your knowledge does. The observable universe is like that illuminated sphere. James Webb is a brighter flashlight than we have ever built, but it does not remove the fog. It only pushes it back slightly, revealing that the fog is thicker, deeper, and more extensive than we assumed. One of the most unsettling implications of this is that our location in the universe may not be special, but it is certainly limited. We observe the universe from one vantage point, at one moment in cosmic history. The universe we see today is different from the universe that existed 10 billion years ago, and it will be different again 10 billion years from now. As dark energy drives accelerated expansion, more galaxies will slip beyond our observable horizon. Future astronomers, if any exist, will see a quieter, emptier sky. James Webb is capturing a fleeting era when the universe is still rich with visible structure. In that sense, its images are not just scientific data. They are historical records of a cosmos in transition. When people ask whether the universe is finite or infinite, they are often imagining a yes or no answer. But the reality may be more subtle. The universe could be finite but unbounded, like the surface of a sphere where you can travel forever without encountering an edge. Or it could be infinite, extending endlessly in all directions. Or it could be something even stranger, with a topology that defies simple visualization. James Webb does not settle this debate, but it constrains it. By measuring the geometry of space and the distribution of matter at extreme distances, Webb helps narrow the range of possibilities. So far, the evidence suggests that the universe is very close to geometrically flat, which is consistent with both extremely large finite universes and infinite ones. In practical terms, if the universe is finite, it is so vast that its curvature is undetectable within our observable region. This brings us back to the emotional core of the question. Why do we care how big the universe is? We care because size implies context. If the universe is small and closed, then everything that exists is part of a single, contained story. If it is vast or infinite, then our story is one among countless others, unfolding in parallel beyond any possibility of contact. James Webb is not telling us which of these is true. It is telling us that whichever answer we eventually approach, it will not be comfortable or simple. The universe is larger, older, and more indifferent than our intuition suggests. And yet, within that immensity, it has produced stars, planets, chemistry, and consciousness capable of asking these questions at all. As we move deeper into this documentary, we will explore how James Webb measures distance, how cosmologists translate faint light into maps of spacetime, and how the concept of size itself begins to dissolve at the largest scales. For now, what matters is this: the universe does not end where our vision ends. James Webb has not found the edge of everything. It has found the edge of what can be revealed by light. And beyond that edge lies a reality that may be far larger than any number we can meaningfully comprehend. To understand what James Webb is truly telling us about the size of the universe, we need to understand how distance itself is measured in cosmology. Because in space, distance is not a simple ruler laid end to end. It is elastic, it stretches, it evolves. And the farther we look, the less intuitive it becomes. When James Webb detects a galaxy near the edge of the observable universe, it is not seeing that galaxy where it is now. It is seeing where it was billions of years ago, when the universe was young, dense, and dramatically smaller. The light has been traveling ever since, while the space between us and that galaxy has continued to expand. This creates a paradoxical situation in which an object can be observed at a distance of 13 billion light-years in terms of light-travel time, yet be more than 40 billion light-years away in terms of present-day separation. This is not an error or a trick. It is a direct consequence of living in an expanding universe. For most of human history, distance meant something straightforward. If you walked for a day, you covered a certain number of miles. If you sailed for weeks, you crossed an ocean. Even early astronomy extended this logic. The stars were farther than the planets farther than the moon. But once Edwin Hubble discovered in the 1920s that distant galaxies are moving away from us and that their speed increases with distance, it became clear that space itself is dynamic. Galaxies are not flying through space like shrapnel from an explosion. Space is stretching, carrying galaxies along with it. This distinction is subtle but crucial, because it means that there is no central point of expansion and no outer boundary that is expanding into something else. The universe is not expanding into empty space, it is expanding everywhere all at once. James Webb operates within this framework, but with unprecedented sensitivity. By observing infrared light, Webb can detect galaxies whose visible light has been stretched or redshifted by the expansion of the universe into wavelengths too long for earlier telescopes to see. Redshift is more than a color change. It is a record of cosmic history. The greater the redshift, the longer the light has traveled, and the more the universe has expanded during that journey. By measuring redshift with high precision, Webb allows astronomers to place galaxies on a cosmic timeline, reconstructing how space itself has grown. What makes this especially important for the question of size is that the expansion of the universe is not uniform over time. In the early universe, Expansion was dominated by matter and radiation, slowing gradually under gravity. Then, several billion years ago, dark energy began to dominate, causing the expansion to accelerate. This acceleration creates an event horizon, similar in concept to the horizon around a black hole. Beyond a certain distance, galaxies recede from us faster than light can travel through the expanding space between us. Light emitted from beyond that horizon today will never reach us, no matter how long we wait. That horizon defines the maximum size of the observable universe in the future, not just now. James Webb is observing galaxies that are perilously close to this boundary. Some of the light it detects left its source before dark energy began to dominate, when those galaxies were still within a region of space that could eventually communicate with ours. Today, those same galaxies may already be beyond our cosmic event horizon, permanently cut off. This means that Webb is, in a sense, seeing the last light we will ever receive from vast regions of the universe. That realization reframes the telescope's discoveries. These are not just distant objects. They are fading connections to parts of reality that are slipping away forever. The methods used to translate these observations into distances are intricate and layered. Astronomers rely on what is known as the cosmic distance ladder, a series of overlapping techniques that build upon one another. Nearby distances are measured using parallax, the apparent shift of stars as Earth orbits the Sun. Farther out, standard candles such as Cepheid variable stars and Type I supernovae provide reference points because their intrinsic brightness is known. At the largest scales, redshift and models of cosmic expansion take over. Each rung of this ladder introduces uncertainties, and those uncertainties compound as we look farther back in time. James Webb does not eliminate these uncertainties, but it reduces them by providing clearer, more detailed data than ever before. One of the most profound contributions Webb is making is refining our understanding of the Hubble constant, the rate at which the universe is expanding today. There has been a persistent tension in cosmology between measurements of the Hubble constant based on the early universe and those based on the local universe. Early universe measurements, derived from the cosmic microwave background, suggest a slower expansion rate. Local measurements, based on nearby supernovae and galaxies, suggest a faster one. This discrepancy is not small. It is statistically significant, and it hints that our model of the universe may be incomplete. James Webb's ability to observe distant galaxies and supernovae with high precision offers a way to test these measurements and potentially resolve the tension. Why does this matter for the size of the universe? Because the expansion rate determines how quickly the observable horizon grows and how much universe is accessible over time. A faster expansion means a smaller observable fraction of a potentially much larger whole. A slower expansion means more of the universe remains within reach. If the Hubble tension reflects new physics, such as unknown forms of energy or modifications to gravity, then our estimates of the universe's size and fate may need to be revised. Webb is not just measuring distant galaxies. It is probing the foundations of cosmological theory. As astronomers analyze Webb's data, another pattern is emerging that complicates the picture further. The distribution of galaxies at extreme distances appears more clumpy and irregular than expected. This could be due to observational biases, or it could reflect genuine features of the early universe. If the latter is true, it suggests that the large-scale structure of the universe may vary more from place to place than our models assume. In an infinite or extremely large universe, such variations would be expected. Our observable region might be relatively typical, or it might be unusual in subtle ways we are only beginning to detect. This raises a delicate philosophical issue that science cannot avoid. When we infer the properties of the entire universe from a single observable patch, we are making an assumption known as the cosmological principle that on large scales, the universe is homogeneous and isotropic, meaning it looks roughly the same everywhere and in every direction. This assumption has been remarkably successful, but it is still an assumption. James Webb's deep field observations are pushing that assumption to its limits by sampling regions of space and time never before observed. If deviations from homogeneity are confirmed, they would not invalidate cosmology, but they would force us to confront the possibility that our cosmic neighborhood is only one realization among many. In practical terms, this means that asking for the actual size of the universe may be like asking for the total area of an ocean when you can only explore a few square miles. You can infer properties, estimate scales, and build models, but you cannot be certain that what you see is representative of the whole. James Webb does not remove this uncertainty. It makes it explicit. By revealing how complex and unexpectedly mature the early universe appears, Webb suggests that the cosmos may be richer and more varied than our simplified pictures allow. Another subtle but crucial point is that the universe's size is not static even in principle. Because space itself expands, the distance between any two sufficiently separated points increases over time. The universe today is larger than it was yesterday, and it will be larger tomorrow. This expansion does not require new space to be created at an edge. It happens everywhere. So when we talk about the size of the universe, we must specify when. The observable universe at the time the cosmic microwave background was emitted was much smaller than it is now, even though it contained the same amount of matter and energy. James Webb, by observing different epochs simultaneously, gives us a layered view of this growth. There is also a deeper issue lurking beneath these measurements, one that touches on the nature of space itself. In general relativity, space is not a passive stage on which events unfold. It is an active participant shaped by energy and matter. The geometry of the universe determines how distances behave, how light travels, and how volumes scale. If the universe has a complex topology, with connections or identifications beyond simple three-dimensional space, then its total size could be finite even if it appears infinite locally. James Webb cannot directly detect such topology, but its measurements constrain the possibilities by limiting how much curvature or repetition could exist within the observable region. As the data accumulates, a picture is forming that is both clearer and more unsettling. The observable universe has a well-defined size set by the age of the cosmos and the dynamics of expansion. Beyond that lies a vast expanse that is not empty, not hypothetical, but simply inaccessible. The actual size of the universe could be only slightly larger than what we can see, or it could be unimaginably larger, perhaps infinite. James Webb is not delivering a final answer because there may be no final answer to deliver. Instead, it is revealing the structure of cosmic ignorance, showing us where knowledge ends and inference begins. This realization does not diminish the achievement. On the contrary, it elevates it. For the first time, humanity has an instrument capable of directly observing the era when the universe's large-scale structure was taking shape. We can watch galaxies assembling, stars igniting, and black holes growing at the dawn of time. We can test our theories against reality at scales once thought forever beyond reach. And in doing so, we are forced to confront the possibility that the universe is not just large, but fundamentally larger than any observation can confirm. By the time James Webb peers to the deepest edges of cosmic time, a final truth begins to emerge, not as a number, but as a perspective. The universe is not something with a clearly marked boundary waiting to be measured. It is a process unfolding through expansion, governed by forces that remain mostly invisible. Dark matter provides the gravitational scaffolding on which galaxies form, while dark energy drives the accelerating expansion that steadily pushes vast regions of space beyond our reach. Together, they determine not only how the universe grows, but how much of it can ever be known. James Webb does not see dark matter or dark energy directly. What it sees are their consequences written into the shapes of galaxies, the bending of light, and the timing of cosmic evolution. The surprisingly rapid formation of massive galaxies hints at dense concentrations of dark matter guiding matter into structure early in the universe's history. The fading visibility of distant regions reflects the quiet dominance of dark energy, stretching space so relentlessly that the observable universe becomes a shrinking island within a far larger cosmic ocean. What this means is that the actual size of the universe may be less important than the limits it imposes on knowledge. There are places that exist but cannot be observed, events that occur but can never influence us, and structures that shape reality while remaining unseen. James Webb reveals these limits with unprecedented clarity. It shows us a universe that is generous in beauty and complexity, yet strict in what it allows us to access. In the end, the universe does not offer closure, it offers scale. It reminds us that even at the peak of our technological reach, we are still embedded within something vastly larger than ourselves. James Webb has not finished the story of the universe's size. It has revealed that the story may not have an ending at all, only horizons that recede as we approach them, and a cosmos that continues to grow silently and endlessly beyond the furthest light we will ever see.